In last week, we learned how to interpret the regression results. We interpret the estimator beta 1 hat as an increase of 1 unit of x is associated with an increase of beta 1 hat units of y. Notice that we use association, not causation. We don't say 1 unit of x causes beta 1 hat units of y. The reason is that linear regression estimators only describe the correlation, not causation. We also learned that if we change the scale of x or y, how does that change the estimators and their interpretations? In the second video, we learned the goodness of fit, the R-square. It describes how much the total variation in sample can be explained by the fitted model. We derive R-square equal to SSE over SST, which is equal to 1 minus SSR over SST. Remember that SSE is the explained sum of residuals. And the SSR is the residual sum of squares. And the SST is the total variation of the observation yi. The derivation of this equation depends on some properties regarding the sample mean of the residual, the covariance between x and the residual u hat, and the covariance between the fitted value y hat and the residual u hat, all of them equal to 0. In the third video, we learned what does the linear means in linear regression models. It's linear in the parameters, not in the dependent or the independent variables. Therefore, we can easily incorporate nonlinear relationships into the simple linear regression models. Here are some examples. For example, we can consider the linear log model, quadratic form or cubic form, or log-log model. Once you have a sample and you estimated the parameter beta 1 hat, make sure you know how to explain this beta 1 hat. In this week, we will learn some statistical properties of the estimators. Why linear regression models are so popular in empirical studies. Besides the reason that they are simple enough, they must have some nice properties for the estimators such that we can trust the conclusions based on these estimators. This video, we will focus on the expected values of the OLS estimators. In next video, we will consider their variances. If you think about it, what kind of the expected values of the OLS estimators and the variance of the OLS estimators are ideal? For the expected values, we would want them to be as close to the true parameter beta as close as possible, and for the variance, we would want it to be as small as possible. In this video, we will show the unbiasedness of the OLS estimators. That is, the expected value of beta 0 hat is equal to beta 0, and the expected value of beta 1 hat is equal to beta 1. And for the next video, we will derive the variance of beta 0 hat and the variance of beta 1 hat. These nice properties are often obtained under certain assumptions. Recall our assumptions for the linear regression models. Let's formally list them here. The first one is that we have the correct specification. More specifically, the regression model should be linear in parameters. The second assumption is the random sampling. It means if we have a sample consists of n observations of xi and yi, this sample must be randomly drawn from the population, which consists all the observations you can imagine for this model. The third assumption is that there must be some variation in x. Mathematically, it means the variance of x is not equal to 0. Imagine that this variance of x is equal to 0. It means this x is a constant. So it's corresponding to the case that we have the x is the constant, but y could be here. If you regress it, we cannot find a beta 0 hat and beta 1 hat if the variation of x is equal to 0. The last assumption is the zero conditional mean, which is that the expectation of the arrow term u conditional on x is equal to 0. A kind of implication from this assumption is that the expectation of u is also equal to 0. The reason is that by the iterated law of expectation. So the outer expectation is taking on x. So because the inside this here is 0, so the total expectation is also equal to 0. Under these four assumptions, we have the theorem 1, which is about the unbiasedness of OLS estimators. That is, the expectation of beta 0 hat is equal to beta 0, and the expectation of beta 1 hat is equal to beta 1 for any values of the true parameter beta 0 and beta 1. In other words, the OLS estimators beta 0 hat and beta 1 hat are unbiased estimates for the population parameter beta 0 and beta 1. Before proving this theorem, we need to make sure that we understand this theorem. I still remember that when I first learned this theorem, I was quite confused why we can take expectations on beta 0 hat and beta 1 hat. When we use the operation of expected values, we often take expectations on some random variables. What is a random variable? For example, if you throw a dice, the outcome is a random variable. It can take value from 1, 2, 3 to 6, and each value has some probability of 1 over 6. So we can take the expectation of the outcome of throwing a dice, which is 1 times 1 over 6 plus 6 times 1 6, which is equal to 3.5. But here, if we take expectations of beta 0 hat and beta 1 hat, it means beta 0 hat and beta 1 hat are also random variables. Similarly to the outcome of the dice, they can take many possible values and each value may have some probability. But why they are random variables? Where the randomness come from? The answer actually depends on the difference between the population and the sample. We briefly talked about the population regression function and the sample regression function. In the population regression function, y equal to beta 0 plus beta 1 times x plus the arrow term u. These beta 0 and beta 1 are the fixed parameters, but we just don't know their true value. So we collect data and estimate this beta 0 hat and beta 1 hat to approximate this true parameter, to get some idea about what this true parameter will be. Given a new sample, we will have a new beta 0 hat and a new beta 1 hat. In other words, these two parameters are some kind of function of the sample x and y. Indeed, it is the case if you write down the formula for beta 0 hat and beta 1 hat. For example, beta 1 hat is equal to the covariance between x and y divided by the total variation of x. So you can treat it as beta 1 hat as a function of xi and yi. I is equal to 1 from n. So by the assumption 2, we have the random sampling. So the x and y are random variables because they randomly draw from the population. Once you draw, you know x and y is. But before you draw, you don't know their values. So you can treat it as random variables. Because x and y are random variables, the beta 0 hat and beta 1 hat are also random variables. So the randomness comes from the assumption that the sample is randomly drawn from the population. We will continue to prove the theorem 1 under the assumptions 1 to 4. First, from the first assumption, we can write down the population model in terms of a random sample xi and yi. The sample size is n. Notice the difference between the error term ui and the residual ui hat. The error term ui is from the population model. It contains unobservable factors that affect yi, but the residual ui hat is the difference between the observation yi and the fitted value yi hat. Given the random sample, we've already derived before that beta 1 hat is equal to the covariance between xi and yi divided by the total variation of xi, and the beta 0 hat is equal to y bar minus beta 1 hat times x bar. Notice that here xi, yi are all treated as random variables. Since the independent variable x is the observed factors and the error term u is the unobserved factors, we often fix x and only consider the randomness implied in the unobserved factors. We want to prove that conditional on x, the expectation of beta 0 hat is equal to the true parameter beta 0, and the conditional expectation of beta 1 hat is equal to the true parameter beta 1. We first simplify the formula for beta 0 hat and beta 1 hat. From the formula of beta 1 hat, we first replace this yi with the population model, which is beta 0 plus beta 1 times xi plus ui. Then we expand the numerator. Then we have these three terms. Notice that beta 0 and beta 1 are the true parameters. They are fixed, so they can take outside of this summation. The denominator is denoted as the total sum of squares of x, which is SSTx here. Notice that this first term is equal to 0 because the summation of xi minus x bar is equal to 0. The second term here, summation xi minus x bar times xi is equivalent to the summation of xi minus x bar, take the square. So we only have beta 1, which beta 1 here. And the third term is the covariance between the xi and the arrow term ui. If we denote the deviation di equal to xi minus x bar, which is the deviation for each xi, then we have the third term is this term. So in other words, beta 1 hat is equal to a fixed parameter beta 1 plus some linear combination of the arrow terms. Conditional on x, The randomness in beta 1 hat is entirely driven by the error term in the sample. This error term ui can be larger than 0 or smaller than 0, which makes the beta 1 hat higher or smaller than the true parameter beta 1. Similarly, beta 0 hat equal to the y bar minus beta 1 hat times x bar. This y bar is equivalent to beta 0 plus beta 1 times x bar plus u bar. And we put this x bar together, then we have the simplification for the formula for beta 0 hat. Given these two simplified formulas for beta 1 hat and beta 0 hat, we take expectations of beta 1 hat and beta 0 hat. Notice that this expectation is taken over conditional on x, which means you can treat x as something you've already known, so every term about x can take outside of the expectation operation. So here, like the SSTx, which is total sum of squares for the xi, it's all about the x, so we can take outside of the expectation, which is here. And about this di can also be taken out of the expectation because the di is the xi minus x bar. All of them is also about the x. So notice the assumption for EU conditional on x is equal to 0. So it means for any ui, this term is also equal to 0. So we only have beta 1 left. It means the expectation of beta 1 hat conditional on x is equal to the true parameter beta 1. Similarly, for beta 0 hat, the beta 0 is a fixed number, so its expectation is itself. Here, this term, x bar can be taken outside of the expectation operation. The expectation of u bar conditional on x is also equal to 0. You can write down this u bar is equal to 1 over n ui divided by n, conditional on x, because the assumption for this holds for all I from 1 to n, so this term, if you replace here, this term is equal to 0. Then we only have beta 0 left. So the conditional on x, the expectation of beta 0 hat is also equal to beta 0. These two prove the unbiasedness of OLS estimators. What if the assumptions fail? If any of the assumptions fails, the linear regression estimators will be biased, and we may not trust the regression results. Therefore, we need to check or argue these assumptions before using linear regression models. But luckily, the assumption 1 to 3 generally are not big problem. The assumption 1 about the linearity in parameters. We've already learned that even if the relationship between x and y are not linear, we can still use log, quadratic, cubic or to capture these nonlinearities. The assumption 2 about the random sampling generally holds for cross-sectional data. The assumption 3, the variance of x, is not equal to 0. It usually is not a big problem, but the assumption 4 is the one that we should be careful. It is very likely to fail because the error term u captures all unobserved factors. It's very easy to have some factors that correlated with the observed factor x. We've already discussed some examples in the introduction. So here is a real-world example showing that if zero conditional mean fails, we may have suspicious regression results. Suppose the econometric model is to study the relationship between the math performance and the school lunch program. The dependent variable math 10 is the percentage of 10th graders passing a standardized math exam for each school. And the independent variable lunch program is the percentage of students who are eligible for the free lunch program. A reasonable hypothesis is that if a school has a higher coverage for the lunch program, more students are eligible to have free lunch, then there should be a positive effect on the performance on passing the math exam. In other words, our hypothesis is that beta 1 hat should be larger than 0. Here is the code in R. We first get the data from a package called Woodridge. It contains all the data sets for the textbook. We find the data MEAP 93. Then we can run the regression LM. The first argument is the formula, which is the dependent variable over independent variable x. Then we call summary to check the regression results. Beta 1 hat is equal to minus 0.32. It means that a higher coverage of lunch program is associated with a decrease in the performance on the math exam. Can we trust these results? The results is not trustable is because the assumption 4 is likely to fail. For example, consider these unobserved factors. U, the error term, contains the poverty rate of the students in the school. Schools with more poor kids are more likely to have higher coverage of the lunch program, but these schools are also likely to have low performance on passing the math exam. Therefore, the unobserved factor, which is the poverty rate, is likely to correlate with the coverage of the lunch program.